Welcome back to the course Collaborative Robots Theory and Practice. In this lecture, we will discuss inverse kinematic analysis of universal robot arms. It looks like this, you see. It has first axis that goes like this, okay, and then you have second axis, you have third axis, you have fourth axis, fifth and sixth, and finally this is your end effector. So, working with this kind of robots, there are many which are having similar architecture. You see, so it has not more than two consecutive axes which intersects at a point. So, it does not have a wrist which has three axes all intersecting at a single point over here somewhere. Okay, so it does not have a wrist which is a single wrist. So, instead it has wrist which may be divided into three different wrists. Okay, so if this is your axis and this is your axis, this is one, okay, and then you have another axis which goes like this, okay, and finally this is your end effector. Okay, so this may be one axis also which is not intersecting, though you can call it wrist 1, wrist 2 and wrist 3. So, all together in quite a lot of robot, at least in case of industrial robots, you will find they intersect all the three axes, they intersect at a point, and we call it a combined wrist center point. So, that is axis 4, 5 and 6, they intersect at a point, okay, and that is wrist center point. We have seen it earlier. Okay, so in this robot that is not the case. So, it is like a snake kind of robots, and you see all the UR arms, UR here I would mean universal robot arms like UR3E, UR5E, 10E, 16E, 20 and now 30. So, all the UR arms are of this configuration. So, let us do universal robots arms here. So, we will quickly do the forward kinematics first. Forward kinematics we have already done earlier also. So, you see you can directly put all the rotating axes as z axis. So, this is your ground, this is the frame which is attached to the ground, okay, and then you have link 1 ends up with frame 1 and this is your link 2, okay, this is frame 1 and then you have frame 2, link 2 ends up with frame 2, link 3, frame 3, okay. I am placing just the z axis first. So, if this is z0, this is z1, z2, z3, z4, z5, okay, and z6 is at the end, that is over here. So, z5 and z6 they are collinear. So, you have your end effector that lies here. Okay. So, now the common normals to all the z axes are x axis, you know. For the ground frame, this is your x0. So, you have I have preferred putting the forward direction as x axis here. By default UR arm they have reverse direction as x axis, but that I am not considering here. So, I am preferring all the forward direction as x axis. So, this is x0, x1, x2, x3, x4, x5 and finally this is x6, okay. And y axis can be obtained using right handed thumb rule, okay. X cross y should be equal to z. So, z cross x is equal to y. So, you can get y0 like this, y1, y2, y3, y4, y5 and y6 like that, okay. So, now you see you have dh parameters that will go like this. So, distance between two z axes, okay, perpendicular distance, so common normal. So, this should be your x axis. So, from here to here this is your A2, distance measured along z axis is your D. Okay, so that is joint offset. So this is your D1. Okay, rest is your A2, A3, and then again you will have all the D's here. Okay, so it is D4, and this is D5, and this is D6. So all the dimensions can be taken up from the data sheet of this robot. So this is how it look like, and DH parameter table can be made quickly like this. Okay, so alpha is rotating from Z0 to Z1 along x-axis, so it is minus 90 degree here, and similarly other alphas can also be obtained. So these are link twists. So this is how you do forward kinematics. This is very important here, because we will be using transformation matrices taking their inverse at lot of times. So this will be very helpful. So now I have just drawn the stick model of this robot here. So DS parameter table is populated here with the technical specifications of your 5E arm at its default state. Okay, at its default state. So I have put all the default state is when all the x joint angles are 0. Okay, so there is no initial angle. So in DS parameter table anyway that doesn't count here. So it's this configuration what you can see here is actually the default state of this robot at all the joint angles equal to 0. Okay, so I have put all the values here, and this is how it is. So now this is the stick model. So it can further be simplified like this. If I look from the top, this robot may look like this when joint angle theta 1 has rotated by some angle. Okay, so it goes like this. So if I look it from the top, it should look like this. So from here you see this is your joint 0 or 1, both will be 1 over the other. Okay, so that is here, and then you have A2 that is visible here, A3 is here. Okay, and then you have D4. So this is your D4, and then this is your D5. D5 I have assumed it has rotated by certain angle. Okay, and then looking from the top, this distance D5 is visible like this. So this is your D5. Okay, and then you have finally D6. So D6 would come like this, and at the end you have this frame. So all the Z axis, so at least you can see this is Z1, this is Z2, this is Z3. So all of them, that is all the blue ones, so this is Z1, Z2, Z3, they are all parallel to each other, and finally you have Z4, Z5 and Z6. So this is Z6 that comes at the end. So this is how it will look like. Okay, so this figure I will be using it part by part in different parts of this analysis. Okay. So let us recall the forward kinematic transformation. That is quite simple, you remember. So T0 to 6 is the end effector configuration matrix with respect to the frame 0. Okay, that is given as, that is a variable of containing multiple parameters theta 1, theta 2, theta 3, theta 4, theta 5 and theta 6. These are all joint variables. So for any 6 degrees of freedom robot, the homogeneous transformation matrix from the base frame to the end effector frame is defined like this, whereas 0, A1, 1, A2, A3, A4, A5 and A6, these are our link transformation matrix. Okay. So this each one of them are functions of just one joint variable, and remaining are structure of the link d theta a alpha. This comes from the dh parameter directly. Okay, with a variable, joint variable, that is theta 1, theta 2 and so on so forth. Okay, so the link transformation matrix or the total transformation from any point, let us say I to j, is given like this, where the 3 cross 3 matrix is rotation transformation matrix, and this the last column basically that is the position of that point. So, if this is the figure for that, so it transforms from I to j by a position vector p. So, p j with respect to I, okay, along x axis, along y and along z are the projection of position vector p I to j along x, y and z. So, this is the translation that has happened from I to j. So, components of that is reflected in the last column. What about u, v, w? U, v, w are the frame projections. You see, u along x, u along y and u along z. Similarly, v along x, v along y and v along z. W along x, w along y and w along z. So, they all are like this. So, this is how a standard any transformation matrix will have all their components arranged. Okay. So, I will move ahead. So, this is what you already know. So, now inverse kinematic problem of this robot, actually what is given here is end effector position, that is 0, 0, 6. Okay. So, from 0 to 6 that position is known, and the orientation of end effector is also known. So, end effector may be given in terms of Euler angles, maybe roll, pitch and yaw. You can convert it to rotation matrix, okay, the way we have done it earlier also. Okay. So, in the step 1 what we will try to obtain is, given the frame 6, okay. So, I will try to figure out where is my frame 5. Okay. In order to obtain that, this distance, that is d6, so I will convert it to vector. How can I do that? So, if this is the distance d6, so d6 is along z axis. So, d6 may be written as d6 0 0 1, and this is in which frame? This is in frame 5. Okay. Frame 5 or frame 6, both are equally good here. Okay. So, this is already there. So, if you know the end effector rotation matrix for frame 6 with respect to O, this gets converted to this vector which is here is now converted in frame 0. Okay. So, when you, this is in local frame d6, this is in local frame. So, if I multiply this with 0 or 6, it gets converted to, the magnitude remains the same, but the vector is now expressed in 0 frame. Now, the vector triangle is formed. Okay. What is given is 0, 0, 6. This we have already obtained. So, using this vector triangle, okay, I can quickly obtain the location of frame 5 with respect to frame 0. Okay. So, this vector is now obtained. So, this is 0, 0, 5. Okay. This vector is now obtained using this equation. Okay. This is using vector triangle. So, we have obtained frame 5 now. Okay. This is what we have obtained with respect to O. Now, the step 2. Okay. Step 2, what I have done, okay, what is given is 0, 0, 5, that is the fifth frame that we have obtained in the previous slide. Okay. So, I already know my location of frame 5, that is sitting here. Okay. Frame 5. Okay. So, this location is known. So, now if I look from the top, it looks like this. So, you see you have Z1, this is Z2, this is Z3. So, all three are Z1, Z2 and Z3 are visible here. Okay. And then comes your Z4, I assume it has rotated the way it is shown. So, it is Z4, and finally, you have Z5 that comes like this. Okay. Looking from the top, it exactly looks like this. Now we can obtain theta 1. How, you see? So, whatever is the position of 5, we have already obtained 5 with respect to O frame, the first frame, 0 frame, which is attached to the ground. Okay. So, this is known. So, we already know the O 0 O 5 along x and along y. So, these two are known. Okay. Using that, so I can quickly find O5 xy. So, along xy, that means square of this plus square of this, square root should give me this. Okay. So, psi can be obtained directly from this. So, you take this and you take this, you can calculate psi. Now, in the second go, what I will obtain? I will try to obtain this one, phi. This can be quickly calculated using this. Now, we will consider the another triangle. Okay. And in this triangle, you can calculate this. So, this is what? If this is your D4, this also is your D4, this is the right angle triangle. D4 is already known and this we have obtained in the previous go, okay, over here. So, using these two, now I can calculate the angle phi, okay. So, this I have put here. Knowing psi and phi, I can quickly calculate the angle theta 1 like this. Okay. So, theta 1 is equal to psi plus phi minus pi by 2, because this is pi by 2, okay, and psi plus phi minus pi by 2 will give you theta 1. So, this is your theta 1 that can be obtained. So, I will just quickly recalculate. So, psi is equal to, using arc tangent 2, I have used this and I have used this, I calculated psi, okay. Next one is phi is equal to squaring these two and adding and taking a square root, I obtained this side, that is this one, okay. This is equal to D4 from here, okay. So, now I can calculate phi, phi is obtained. Using phi and psi, I have obtained theta 1. So, theta 1 is obtained. You see, it has multiple solution, you see, because this is in plus or minus. If you put it here, this also has multiple solution. Now, moving to next, I will try to obtain theta 5. How will I do it? Again, I will obtain, this is already given, you see 0T6, that is the end effector frame position and orientation is known, that means 0T6 is known, okay. So, that is a product of, now that I have already obtained theta 1 in the previous step. So, what I will do? I will use 0A1, that is transformation matrix from frame 0 to frame 1, that comes here, into transformation matrix from 1 to 6. This is linked transformation matrix. This is transformation from 1 to 6. Okay. So, this equation holds true. 0 to 6 is equal to A 0 to 1 into 1 to 6, transformation 1 to 6. Okay. So, if I take inverse, you can write it like this, and finally you will get something like this. So, this is nothing but, this is quickly obtained using theta 1. I can obtain transformation from 1 to 6. So, now when I know transformation 1 to 6, this is already there 1 to 6. So, component along Z is used here. Okay. Okay, how much is that actually? So, see, this is component along Z. So, whatever is Z1 direction, so in this frame you are looking frame 6, okay, frame 6. So, Z6 component along Z1 is along same direction, okay. So, that will come out to be like this, okay. So, how much is that? So, this whole distance is actually 106 Z. So, whatever is from 1 to 6, okay, from 1 to 6, whatever is the vector, position vector from 1 to 6, the Z component of that will be along this direction, and that is equal to this. So, if this is the vector, let me just draw it. If this is the vector, the Z component is this one, okay. So, that is equated to two things here, okay. I have just cleaned it up. So, this is your Z component which is here. So, that is equal to two things. First is D6 cosine theta 5. So let me just draw it here once again. So if this is your, over here you are measuring theta 5. So whatever this one rotates, that is what is the angle that is made by the D6, okay, D6 branch. So D6 makes an angle. So D6 is something like this. So if this is your theta 5, okay, whatever is D6 over here, that will rotate by an angle theta 5, is it not? So D6 cosine will actually come along Z6 direction, okay. So that projection is now used. So if D6 comes from here to here, so this becomes your D6 cosine of theta 5, okay. So that is visible here, and D4 is the distance already along Z axis. So D4 plus D6 cosine theta 5 becomes the Z projection of 1 to 6, 1 to 6, that is there. So using that I can quickly obtain theta 5, that is equal to this. So this is further extended to this. So now how much is 0A1 inverse, that I have used it here. That is very trivial. So you can just see from the top and you can calculate it manually also. Z projection, this is y, this is x. So if you see your x1 along x0, so it is x1 along x0, x1 along y0, x1 along z0. Similarly y is directed downward, you see in the original figure. So it is y along z, actually it comes along z and downward. So it goes like this, okay. This is projection of, so z1 along x0, z1 along y0, z1 along z0. So that is here, and this is simply the distance from 0 to 1, okay. So it is d1 along z axis. So this can be also obtained quickly. So if you take inverse, it comes to this. This I will be using next. So I have used it here also, okay. So now using this equation here, I have just expanded it using equation 9. So this is your inverse part of it, 0 to t0 to 6, this is t1 to 6, okay. So this was your inverse of 0 to 1, okay. So if I use it, I can quickly obtain this part, okay. So this is what was used here, okay. So that you can quickly obtain. So it is basically this part of this. So you can quickly see it here. It comes out to be this into this, okay. This into this gives you this, okay. So this is how I have obtained that. So now you can recall whole of this quite easily. So what is this now? So D6 projection along this direction is actually D6 cosine theta 5. Theta 5 is the angle moved by this link, okay. So that cosine theta 5, D4 is already along this direction. So total distance along this direction is this, and 1 to 6, this vector projection along this direction is this. So equating both of them, you can obtain theta 5. So we have obtained theta 5 now. We have already obtained theta 1 in the previous step. Here we have extracted theta 5 also, okay. So now obtaining theta 6, okay. Theta 6, you see 3 stages I have shown for 3 consecutive angles, okay. The components of Z6, you see Z6, this is your Z6 in frame 1. So this is your frame 1, okay, is not affected by joint angles theta 2, that is this angle, and this angle, or all the angles which are parallel to that. So they don't affect the projection of Z6, okay, Z6 on Z1, okay. along this direction there should be no change, because it can only change the x and y components, but definitely z along z is not changing because of any of these rotations, as because they are all parallel to each other, that is theta 2, theta 3 and theta 4. So now the third column of homogeneous transformation matrix T1 to 6, T1 to 6 should be this. Let us just derive it geometrically also. So this is the initial first condition when none of the joints have rotated, 5 and 6. Okay. So this is just a function of 5 and 6, because 2, 3, 4 is not affecting it. Okay, and also it is from 1 to 6. Okay, it is from 1 to 6 anyway. So theta 1 is also not affecting it. So 2, 3, 4 is not present here, theta 1 is not there, so it is only 5 and 6 that will come here. That is done. Now let us understand the exact value of that. So this is how all the frames are oriented initially when there is no rotation. Okay, it is in the default state. So Z1, Y6, Y5, Z4 all are just copied to one single location. Okay, now let us say theta 5 has moved. Okay, so what will happen? X5 and X6 comes out of X1, Z5 and Z6 also comes out of Z1. Okay, by an angle theta 5 remains as it is. Okay, so Z4 along Z4, Y5, Y6 and Y1 remains as it is. Okay, this is first rotation, and Z6 actually comes out from here to here. So this is your new Z6 position. Okay, now this Z6 again has second rotation, that is by an angle theta 6. Okay, so what will happen to this theta 6? Basically this will actually pull out Z6 further and bring Z6 to this position. So this is your final Z6. Okay, now I'll project it back and see how much is the projection of Z6 along X and along Y in the frame 1 itself. Okay, so that is what. So what I'll get here is this. When it came out by theta 5, it came here, and in second go it came here. Okay, so the projections I have written it here also. So same comes at these two locations. So it is actually a unit vector. So you will see only the sin theta 5 cos theta 6 as Z6x. Similarly Z6y will be sin theta 5 sin theta 6. So theta 6 can be obtained by these two. Okay, so that is written as arc tan 2 Z6y by sin theta 5, Z6x by sin theta 5. So I could have striked it off, but yes, that helps me to understand when it is not solvable. Okay, so theta 6 is not well defined when sin theta 5 is equal to 0, or when both of them becomes equal to 0. That is when Z2, Z3, Z4, Z6 are all parallel. In this case there are 4 degrees of freedom. Okay, all the 4 to determine the pose of the end effector in the plane that results in infinite solution. Okay, let me just vanish for a moment. Okay, so this is how I have obtained theta 6. So what all angles I have obtained? I have obtained theta 1, theta 5 and theta 6 now. Okay, now solving for theta 2 and theta 3. Where are they? It is here and here. Now using equation 7, what was that? T1 to 6. So T1 to 6 was already there, in which if I post multiply this with inverse of this, so actually T1 to 6 would go like T1 to 4 into A4 to 5 and A5 to 6. So this can be taken up here and this is written. T1 to 6 was already given because you already have the end effector position and orientation. So this was known. These two can be evaluated using theta 5 and theta 6. So what I now know is T1 to 4, okay, from one frame to the fourth frame, that transformation is now known, the values I have. The origin of the third frame, that is 1 to 3, okay, from here to here can be obtained in a similar way. You have to come back by D4 vector. D4 vector was in this frame, okay, local frame. So multiplying with 1 to 4, that can be obtained from here, okay. I can quickly create a vector triangle the way we did it, and I can obtain O1 to 3. So this is the vector that connects from frame 1 to frame 3, okay. Now this further reduces it to a 2R manipulator. If you look carefully, so from 1 to 3, this is first link, this is second link, okay, that ends here with link length A2 and A3, okay. So it is a 2-link problem. It's a planar manipulator in this frame, in first frame, okay. So it can be quickly solved the way we did it for 2R manipulator, okay. So that is used here, using the previous method only. You can refer to the lecture 1 for 2R manipulator, and I have obtained theta 3, and similarly I have obtained theta 2. 2 and 3 are obtained, okay, using 2R subset of this manipulator. Now all the angles are known except angle theta 4. How to go for it? So from equation 11 that we have seen, okay, we already had T1 to 4. So I'll further take inverse of 1 to 2 and 2 to 3, because we already know theta 1 and theta 2 here. So using that I can take inverse, and I can quickly find out T3 to 4. Where is it? From 3 to 4, okay. So if I know T3 to 4, what I can do, theta 4 is simply but it is this, okay. From 3 to 4, x projection along x, projection along y, these can be obtained from this, okay, from this, and that helps me to find out the joint angle theta 4. Got it? So if this is your x, okay, so x basically rotates by an angle theta 4 like this, okay, this is theta 4, okay. So x rotates by an angle theta 4 like this. So next x, it is the x4, comes out by angle theta 4. Projection of x4 on x3, projection of x4 on y3, okay, y3, okay, are utilized here, okay. So that can be obtained. So that is the first column of this matrix basically, okay. So I obtained theta 4 also. So now overall, with all the combinations of multiple sub solutions, so all the solutions, they had 1 or 2 solutions, okay. So if I combine them all together, your arm has 8 solutions for a given pose, okay. Not all may be possible due to the kinematic limitations or the joint limits that are there, okay. So with that I have obtained all the joint angles theta 1 to theta 6 for your arm kind of, there are many other similar arms, not just UR has all the variants on this architecture only, but there are many similar arms also, okay. For all of them you can use the same technique and find out the inverse kinematics, okay. That's all for this lecture. So in the next lecture I will discuss differential motion analysis, robot Jacobian velocity and acceleration analysis. That's all. Thanks a lot.